So, work. In English, Nick, if you say, I'm doing work, Mr. Duke, what you really mean is, I'm getting tired. In physics, work has nothing to do with tiredness. Work has a very, very specific meaning, a very specific definition. TJ, you do work on an object in physics. You do work on an object, which means just standing there, you're not really doing any work. You have to be doing work on something. And specifically, two things have to happen. A force must act on the object, and the object must move through a distance in the same direction as the force. Let me say that again. A force must act on an object, and an object must move through a distance in the same direction as the force. TJ, can you stand up, my friend? Can you do me a favor? Can you walk over to that wall right there, and can you push against it? Dead serious. Try and push the wall over. Hard, two hands. Okay? Keep going. No, keep going. I want you to keep going. Keep pushing, keep pushing. Now, keep pushing while I'm talking. If TJ kept this up for an hour, he would feel fatigued. And he might even try to argue with me and say he was doing work. Is he applying a force to the wall? Yes. Is the wall moving a distance? No. Under physics, he's not doing any work. Okay? Thank you, TJ. You can sit down. Doug, Enzo, can I borrow you two guys, please? Doug, can you stand right here? Enzo, right behind him. Face that way. On his back, piggyback. Okay, now just stand here. What direction is the force that Doug is having to exert on Enzo? Because gravity is acting. Walk. Right now, Doug is doing no work. Now, he may be saying, Mr. Duick, I'm going to feel tired in an hour, but because the force that he's having to resist is down, gravity, but the direction that he's walking is horizontal, in physics, he's not doing any work on Enzo. That's a key concept. Turn around, go back. If he kept this up for an hour, he might be sweating, he might be fatigued. That's not work. Have a seat. Okay? Work is very specific. It's force times distance in the same direction as the force. It's a scalar, which means no direction, and it's calculated by force times distance. As long as the force and the distance are in the same direction. What are the units for work? Well, what do I measure force in? What do I measure distance in? So, I guess technically it's a Newton meter, but we've given that a name. We measure work in joules. Symbol, capital J, named after a scientist whose last name was Joule. Work is measured in joules. For example, you might ask, how much work does it take to lift a 12-kilogram mass from the ground to a height of 9.5 meters? And one of the key words in this question is that word right there. Which way, what direction are we moving this mass? Vertically, so which force are we resisting? Which force are we having to exert? Gravity. Work is force times distance, but now specifically I can say the force is Fg. Oh, we're going to stay on the Earth, Enzo, so don't be going big G, big M, little m over r squared. We're going to use our shorter, abbreviated version for gravity here on the Earth. We're going to say, hey, that was just mg, where g was 9.8. Times distance, although it's traditional in physics, if you're talking about a short vertical distance, we call that a height. So often you'll see this written as mgh. This is the work done lifting something against gravity. What's the mass? 12 g, 9.8. Height, 9.5. How many joules of work? Crunch the numbers, please. 1,117.2 joules. Let's go 1120 joules. 12 kilograms, around 25 pounds. You know what? Think a little toddler, like if you've got a young niece or nephew, a very small toddler, about 2.5 or 3 years old. 9.5 meters. about 3 sets of stairs, 3 stories. Is it really hard to carry 12 kilograms up 3 flights of stairs? Not really. 1,000 joules, Amanda, not much work. All of us are capable of doing that, probably without even breaking out in a sweat. Elijah pushes against a brick wall as hard as he can for 12 seconds, and the wall does not move. How much work has he done? 0 joules. Why?
Didn't move.
Since D equals 0. Yep. You know what? I think I hit O instead. You know what? There you go. There. What about if we, example 3, to push a box along the floor requires a steady force of 22.5 newtons. If you push it for 13.6 meters, how much work have you done? I think it's reasonable to assume here, Nick, that if you're pushing something and it's sliding along the floor, I think you generally push in the direction that you slide. Same direction. All right. They gave me the steady force. Now, to get that number, 22.5, what I really did on a separate piece of paper is I made up a mass, I made up a coefficient of friction, I went mg down, get the obvious one, normal force up. Who's winning? Applied force. Who's losing? Friction. And I found this is really the net force that I've given you when you went winner minus loser equals what? Don't need to bother doing that because I gave it all for you. Force times distance. How much work? 306 joules. Example 4. Dylan pedals his bike up a 19-meter high hill. You know what? Let's label that. That 19 would go right there. Is that beep coming from these stopwatches? Are you hearing a beep every so often? I think it's from that, maybe. I'll try and figure it out. Anyways, bike requires a steady force of 124 newtons to continue up the hill, so we're going this way. And it says that the hill is at a 12-degree angle. How much work? Can I go 124 times 19? Because that is a force times a distance. Why can't I? Not in the same direction. Now here's the nice thing. Work is a scalar. No matter what the angle is, if I can figure out the vertical distance, which they told me 19 meters, and if I can figure out the force, when I go up a hill, what force am I resisting? Gravity. Now, when I typed this question, I forgot to add one key piece of information. Let's add this. Let's say that the mass is 65 kilograms, and I'll change that next year. What that means is the work is gravity times the height that we go up. Mass acceleration height. Now here's what else that means. K-Van, if the hill was this steep, I'd do the same amount of work. If the hill was this steep, I'd do the same amount of work. Which hill is easier to go up? A shallower hill or a steeper hill? Shallower hill. Which hill would take longer to go up? A long, shallow hill or a short, steep hill? That's what we mean by tiredness. Tiredness isn't the amount of work you do, it's how quickly you do that amount of work. This is why a steep set of stairs will tire you out. A long, shallow set of stairs, which will take you probably 3 times as long to walk, you won't be huffing and puffing at the end. Energy, work, is a scalar. What's the answer? 12,100? I'll go to 3 sig figs because that's about as accurate as we can really be. So one of the nice characteristics about work is it's a scalar as long as you have your force and direction in the same direction. We're good to go. What if the work force isn't constant? What if the force, Brad, is changing? So what if, for example, you're pushing something and you're pushing harder and 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 harder? Or if you're getting tired and you're pushing weaker and weaker and weaker and weaker and weaker and weaker and weaker, then force times distance no longer works because force times distance requires a constant force. So we're going to give you a second definition of work. Work is 2 things. Work is force times distance as an equation. Work is also the area under a force versus displacement graph. Work is also the area under a force versus displacement graph. Like this graph here. Nick, the question asks, how much work was done in moving the object from 2 meters to 5 meters? Can you see, Nick, for the first 2 meters, the force is flat, it's constant. In fact, I can tell you how big it is, it's 2 newtons. But then all of a sudden, when I get to 2 meters, apparently we're kicking it into overdrive. Maybe a rocket has turned on or something, and it's firing with more and more and more increased thrust. I don't know. All I know is the force is getting bigger. And they want to figure out how much work to get from here to here. I can tell you. It's going to be this area. Now, I always pause here, Chris, and I ask, because some of you are wonderful nerds. First of all, what shape is that red shape? What do you call a shape that has 2 parallel sides and 2 sides that aren't parallel? Cool. You're right. Say it loud. It's a trap. That's a trapezoid. Usually you see a trapezoid drawn like this, but better. But this is a trapezoid. So, does anybody know the equation, the formula for the area of a trapezoid? There is one. And I always ask, in fact, this morning I had a kid who knew it. It's only the second time someone has known it. It's obscure, and there's a reason it's obscure, but I always ask to see if someone does have it. I don't think it's on your formula sheet. Good thought, eh? You know what? It may be, but I'm not even, I don't even know if they teach it in grade 10. Maybe they do. Do they? Because it's a redundant equation. It's a redundant formula. You can survive just fine without it. And the reason you can survive just fine without it is as follows. Pick your pencils up and do this. What shape is this trapezoid really? It's 2 smaller shapes. What are the 2 smaller shapes? A square? He got the trapezoid word. Give him a break. A triangle and a rectangle. In fact, you know what, Cole? Let's call this area 1 and let's call this area 2. And because we have drilled into you triangles and rectangles, there's really no need for a trapezoid equation. Although it is quite cool. In fact, the equation for a rectangle and the equation for a triangle come out of the trapezoid equation, for what it's worth, says the math nerd. Pardon me? It's 1/2 a plus b times h over, I think it's that. Or is it a minus b? I have to drive it, to be honest. I've never memorized it because I never use it. I always just draw one line. If you've hopefully picked up, if I don't need to memorize something, if I can just get it in 1 second, I'll just get it in 1 second. It's not worth my brain storing that. What is shape number 1, Cole? So here's my question. Does anybody know what the equation for the area of a triangle is? Ooh, Nick, nice. It's base times height divided by 2. So if you look at this triangle, there's the base. How long? Well, if that's 5 and that's 2, how long is the base? The height is from here to here. Careful, because I don't think we're going up by ones. I know it's 1, 2, 3 squares, but what's each square? What's each hash mark worth? 2. So I think 6 divided by 2. In your head, what is 3 times 6 divided by 2? So the top area is 9. What about the bottom area? What shape is the bottom there, Cole? I think it would certainly be a rectangle. Well played, I say, well played. Hey, what's the area of a rectangle, folks? What's the equation for the area of a rectangle? Length times width. Some people will say base times height again, which is, it's the long times the short, as long as they're 90 degrees to each other. Length times width. What's the length? What's the width? So I think we get this. How many joules of work did we do moving this object from 2 meters to 5 meters? 15 joules. So Doug, I've given you now 2 definitions today. Work is force times distance, and work is the area underneath a force versus distance graph. How do I know which one to use? If there's no graph, don't use the graph one. If there's no graph in the question, trust me, it's force times distance, for now. Turn the page. Power. Definition number 2. Power. Yep. Power. Power is how fast you're doing work. In fact, power, Chris, is what you guys think of as tiredness. When you say, I'm getting really tired, what it really means is you're generating more power than your body is comfortable with. If you generate lots of power, that's when you get fatigued. If you generate a very small amount of power, you can keep that up for a long time. Power is the rate at which work is being done. It's how fast you're doing work. As an equation, it's work over time. It's work over time. It's also a scalar, because work is a scalar and time is a scalar, so how the heck would you get direction from power? Units. Well, what do I measure work in? Joules? It's joules per second, but we've given this unit, because it's so important and common, a special name. Does anybody know what we measure power in? What? 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 I'll never get tired of that joke. Watts. Symbol W. Right now, no, I'll get it to you later, or check the website or whatever. Named after a scientist whose last name was? What? James Watt, as a matter of fact, British guy. Actually not that great a scientist, a fairly good scientist, but a better, in many ways, PR guy. People often think he invented the steam engine. He didn't. What he did was he really improved the steam engine, making it reliable and functional. He's one of the people who helped usher in what you learned about in socials and called the Industrial Revolution. He was one of the people who made steam engines, TJ, reliable enough so that people who up until then had been running factories on people power and horsepower, so they could switch to machine power. In fact, he invented the term horsepower to try and explain to factory workers how many horses approximately his steam engine could replace. Brilliant advertising, because this was about 260 years ago. Do we ride horses much anymore? How many of you own a horse? Do we still measure power in horsepower? It was a good enough advertising unit that even though now none of us have any idea how much work a horse is capable of, we still measure power in it in many ways. Engines measure power in horsepower. So power is a scalar. Example 5. An electric motor is used with a pulley and a rope to lift, you know what, I think that's a key word, to lift a 650 Newton load from the road up to a height of 12 meters. The job is done in a time of 11 seconds. What's the power output of the motor? Power is work over time. TJ, what's the time involved in this question?
11 seconds.
How do you know? You're right.
It says seconds.
Units, right? Have I gone on my rant about memorizing units? If I haven't, I'm going to do it. It's really worth memorizing units. Work. I've given you two definitions for work. TJ, work is force times distance, and TJ, work is the area underneath the force versus distance graph. Is there a graph anywhere in this question? Do you see a graph anywhere in this question? So, okay, you good? What's the can we stop distracting him, or what was happening there? That's what I figured. Okay, you back with me now? Okay. Work is force times distance. Enza, which word did I underline? Which force?
Gravity.
Yeah. So we can really say this. M times G, gravity. Oh, wait. I didn't give you the mass. You know how I know I didn't give you the mass? Because there's not a kilograms in sight.
You gave us the force though.
Oh, I gave you the weight. Remember, we talked about this last unit. I gave you the weight in newtons. I gave you mg. So instead of, you know what? I gave you fg. It's going to be 650, not times 9.8, because that's already in newtons. Times 12, that's force, newtons, times distance, yes? Divided by 11. What's the power output of this motor? $709 watts. That means this motor has a minimum power output of 709 watts. If this was a 500 watt motor, it would be impossible for it to lift a 650 Newton load to a height of 12 meters in 11 seconds. It would take longer. It would take longer. Oh, and you know what? I'm pretty sure that this motor has a power input of way more than that, because motors are not 100% efficient. I'm willing to bet if this is it is an electric motor, I'm willing to bet if you were to measure how much power it's drawing from the plug, it would be closer to 1200 maybe, or 1400. Okay. So, TJ, I wrote down here, note, an often used unit to measure power is the horsepower, invented by James Watt to try and explain to factory workers roughly how many horses his steam engines could replace. Great PR. We still measure power in horsepower for engines, certainly. 1 horsepower is about 750 watts. It's actually, I think, 744. You know what? 750 is a nice round number, close enough. Yeah?
Is this watts same? Can you convert it to the amount of electrical energy, like the same unit in watts?
Ah, that's a great question. Mr. Duick. Yes, Cole. I notice my light bulbs are in watts. Yeah. Well, Mr. Duick, isn't a watt work over time? Sure thing. And isn't it work force times distance? Sure thing. Aha, Mr. Duick! That light bulb's not moving, so how can there be any work? What is moving inside the light bulbs? Electrons. Yeah. In fact, we call the movement of electrons current in amps. Physics 12, we look at electricity and magnet. In fact, we're just about starting with my Physics 12s right now. But yes, there's a completely different equation built on this. What we have to then is come up with, well, what's the electrical force? And yeah.
Electrical devices are measured watts per hour, though? Right?
No, they're watts.
Per second or what?
Can you hold that? Because in about a page and a half, we're going to look at light bulbs.
Sure.
Okay. But yeah, in terms of, because I always have to get every year, hey, if it's force times distance, my light bulbs stand still. Yeah, the electrons don't. They're moving through there like crazy. Trust me. 1 horsepower is about 750 watts. So the motor in my example, I would go like this. 709 watts. I want watts to cancel. I want horsepower on the top. Remember doing these conversion factors way back when, Greg? 1 horsepower is 750 watts. So I guess to go from watts to horsepower, it's going to be divide by 750. How many horsepower is this motor? Just below 1 horsepower, a 1-horse motor. Is that big? No. In fact, 50 horsepower isn't really that big. That's a small car motor, like a smart car or something like that. 200 horsepower. Okay, now you're getting fairly big. That's a good size engine. They go bigger and higher, but power can be measured in watts. Sometimes watts is too small. In fact, 1 watt is not very big. Power can be measured in kilowatts or megawatts. 1 kilowatt is 1,000 watts, 10 to the 3rd. 1 megawatt is 1,000,000 watts, 10 to the 6th, just like the prefixes that are on your formula sheet in that little chart there. Next page. Let's answer Cole's question. The power of a light bulb is the amount of electrical energy it consumes in 1 second. A 40-watt bulb, for example, uses 40 joules of energy in 1 second. In 2 seconds, it uses 80 joules of energy. In 3 seconds, it uses 120 joules of energy. What's the power rating of a bulb that consumes 4,200 joules of energy in 70 seconds? Powers work over time. Let's see. It's using that much energy in that much time. Oh yeah. That's a 60-watt bulb. That's a 60-watt bulb. So we have work, force times distance, or the area under a force versus distance graph. We have power, work over time. We have efficiency. Efficiency basically asks how much bang you get for your buck. It's really how much do you get out compared to how much you put in as a percentage. How much of the energy that we're supplying goes into doing work, and how much is wasted as heat and sound and other dissipative energies. Symbol for efficiency, there is one. I didn't even know this until about 5 years ago. My symbol was always this. EFF, short for the word what? Efficiency. But it turns out, if you take a lowercase n with a tail like that, it's a Greek letter eta, for those of you who are scorekeeping at home, TJ, that's the symbol for efficiency. You don't have to use it. You can write EFF. I'm fine with that. Totally fine with that. Roy, am I a bit of a nerd? Will I choose to use a Greek symbol whenever I can because, oh, it makes me feel more nerdy? Probably.
Is eta right after in the Greek alphabet?
I don't know. I have somewhere a copy of the Greek alphabet, but I've never memorized it. I know it's alpha, beta, delta, it's alpha, beta, gamma, delta. So gamma comes before delta. That's why in science 10, radioactive decay, there's alpha waves, alpha particles, beta particles, and gamma rays. The guy who was discovering radioactivity just named them what he thought alphabetically in Greek, alpha, beta, gamma. He found alphas first, then he found betas, then he found gammas. Then he probably died. Right. Well, you guys, who's the big scientist who did lots of work on radiation, the female scientist? Yeah, Marie Curie. She's actually Polish, but eventually moved to France and then to America. Still the only scientist to win a Nobel Prize in physics and in chemistry. Other scientists have won 2 Nobel Prizes, but in the same discipline. She's the only one to have done it in 2 different disciplines. But she died of radioactive poisoning, and to this day, her diaries have to be kept in lead boxes because when she was discovering all this, she didn't realize that radioactivity is, for lack of a better word, contagious. It causes other things to go radioactive. So Chernobyl actually is doing better than we expected. It's the difference between the theory and the reality. So the theory says this, but sometimes there's factors that you didn't take into account in reality. We're finding more often than not, thankfully, Nick, the Earth is far more resilient than our theory predicted, which is good, because otherwise we really would have botched this thing a long, long time ago. So as an example, the Hiroshima bomb, for example, that was habitable within about 5 years, despite the theory. You pull the dirt out of there, and holy smokes, there's a lot more exchange in atmosphere and rain and groundwater than we really realized, and, oh, good to go. What is efficiency? How do you calculate it? As an equation, it's the amount of work out divided by the amount of work in, or the amount of power out divided by the amount of power in. I don't memorize this equation. Here's what I memorize. Or it's always going to be the smaller number divided by the bigger number. It has been shown that we can't have anything that is more than 100% efficient. It's always less than 100% efficient. However, Aaron, should you discover something and prove that it is more than 100% efficient? Archimedes, Isaac Newton, Albert Einstein, Aaron Freytag. In fact, you know what? Probably Archimedes, Isaac Newton, Albert Einstein. There will be a unit called the Freytag. I guarantee it. You win a Nobel Prize, and you'll probably be, unless you donate it to the world, be able to buy and sell Bill Gates and Steve Jobs. You would solve the energy crisis. But there are various universal laws which show that that ain't happening. That something can't be. The term for that, by the way, you may have heard it, is a perpetual motion machine. When they mention that, what they're saying is it's some kind of machine that once you pull the cord to get it started, you can walk away, and it'll just keep going faster and faster and faster and faster and faster, or keep putting up more energy than you're putting in. Can't be done. So if you ask me the efficiency of something, usually it's pretty obvious what power out and power in is, or what work out and work in is, but not always. I always just remember, you know what, put the smaller number on top in this universe. Oh, but then we want to change it to a percentage, so then we go times 100%. Times 100%. Example 7. A 255 kilogram mass is being lifted straight up. You know what, Enzo? There's that word again, which probably tells me the direction that we're going to be applying a force, yes? At a constant speed by an electric motor. That constant speed is important because that tells me the force is constant, not changing. It's exactly mg. It takes the motor 4 seconds to lift the mass to a height of 12.5 meters. By the way, 255 kilograms. Heavy or light?
Pretty heavy.
Pretty heavy. 12.5 meters. About how many stories is that? How many floors is that?
3 or 4.
One floor is about 3.5 meters. This is about 3.5 or 4 stories. So we're lifting 255 kilograms, about 600 pounds. 4 stories in how many seconds? Big motor or small motor? I'm trying to give you an idea of what big and small numbers are, so that if you make a dumb calculator mistake, you can look at your answer and say, wait a minute, I'm calculating how much power that a little hand crank gave, and there's no way it should be this big. Or I'm calculating how much power a nuclear reactor would give, there's no way it should be this small. So we need to find power in. Hey, that I can see fairly easily. It says the motor is drawing from the plug 10 kilowatts or 10,000 watts. This is probably an industrial strength plug. You may have noticed in your house, most of your power outlets are fairly standard, fairly normal, but for a couple of devices that need higher wattages, you have a special plug. Does anybody know which two devices? That's not the washing machine, gotta be careful. Dryer. By the way, it's any device that has to move an awful lot of heat around. Dryer and what else? Stove, yeah, oven. No, actually, because they designed microwaves to be within a set wattage. You can buy microwaves that require a special plug if you're in a restaurant and you need something industrial. But no, generally, microwaves are around 1,000 watts, give or take. Those your plugs can handle. It's the 2,500 plus watts you need a special plug. So power in, the amount of power that's going into this motor, 10,000 watts. How much power out? Can you see something else in watts anywhere? No? Then let's go to our definition. Power is work over time. It's work over time. TJ, how much time? Woohoo! That feeling right now? It's called success. Isn't it nice? Yeah. Okay. Yep. Lifting, which work is force times distance. There's no graph here, so it's obviously not the area underneath the force resistance graph. Lifting, which force? If you're lifting, which force are we doing work against? Okay, so this is going to be on the top here, mg times the height again. So let's crunch that. Mass, 255. Why did I have to multiply this one by 9.8? Why didn't I have to multiply this 650 by 9.8? I already had. That's why the 650, I'd already done that for you, right? Oh, too far. Height, 12.5 divided by 4. What is the power out? I'll carry a few extra sig figs. It's not my final answer. They didn't ask me to find the power out. What are they asking me to find in this question? Efficiency is it's really whatever the smaller number is, 7,809 divided by the bigger number times 100%. I think this one I can do. I think it's going to be 78.1% efficient if I 78.09, 78.1%, because 10,000 I can divide by in my head. Electric motors are fairly efficient. First of all, nothing is anything remotely close to 100% efficient. Internal combustion engines, car motors, are terrible. Where does a lot of the energy go to? Heat, sound, all that stuff. Okay. The reason that a Prius or a hybrid, even though it has a gasoline motor generating power, the reason it gets such good mileage is that gasoline motor that's generating power is recharging a battery, and it's that battery that is driving an electric motor. You're actually moving the car with an electric motor, and electric motors, the reason they are the future, have a wonderful property. One of the properties, and you'll learn this in Physics 12, of an electric motor is the faster you run it, the colder it gets. It's very counterintuitive, I know, because all of you are used to, in a car, the further down the gas pedal goes, the higher the temperature of the motor goes, the more heat it gives off, not electric motors. This is why they get such great gas mileage. In fact, the faster you're driving with an electric motor, the more efficient it is.
Standard cars are more efficient than automatic cars.
Yeah, but not as much as Nick said standards are more efficient than automatics. Not as much as it used to be. Transmissions in the past 10 years have come an awful long way. Okay, So my first automatic vehicle was a 1973 Toyota Corolla. It had 2 speeds, low and high. Okay, that was not very efficient, because when you were on the freeway and high, I mean, that thing was whining away at a high pitch, just having to really, really, really work. I have a 2010 Santa Fe right now. I think it's got a 5-speed automatic transmission. It's smooth. They also, you know what? I might be able to contradict you. They have designed recently now shiftless transmissions that actually run on a decreasing radius very smoothly, so you don't ever feel a shift. In fact, that's what most of the electric motors do. I would be willing to bet that those are just as, or possibly even more efficient than a standard, because you've removed the human error element.
The automatics too is within it, the fluid rotates, which causes drag.
Oh yeah, there's other sources of energy burnoff. Absolutely. In fact, what we're leading ourselves up to in a couple of classes is what we call the law of conservation of energy, which is one of the top 5 laws of the universe, and it explains an awful lot. It explains why superhero physics is all garbage and that kind of a thing. So electric motors, very efficient. If you're ever using an electric drill, for example, and it starts to overheat, you cool it off by holding it in midair so it's not touching anything and revving it up full. Guarantee that'll cool it off in about 15 seconds. They overheat when you prevent them from turning, when you don't let them rev up full. So that's a nice quality of an electric motor. We're going to pause here. I need you to, got to give you lots of practice on this. So homework, I didn't leave you room to write on this. You kind of have to do this on a separate piece of paper. I was trying to save paper. I think you can certainly do number 1. You can do number 2. You can do number 3. You can do number 4. 5. So far I've done 1, 2, 3, 4, 5. Skip 6. Skip 7 right now. 8. And then in the power section, 2. Gesundheit. 4. 6. 7. And then we have some mixed questions. I think we can do number 1. I think we can do number 2. You'll get some time to work on this Thursday as well, but I'll get you started. I know some of you have various extracurricular stuff, basketball and things. You can spread out the homework as best you can. 3 is good. 4 is good. 6 is good. No. We'll pause right there. Okay.